Okay, 6.2. We're going to spend a couple days on this section. Yesterday we learned about using known identities to simplify other expressions, and we introduced the Pythagorean identity. For all values of theta, sine squared theta plus cos squared theta always equals 1. And then we have two variations of that. So there's actually three Pythagorean identities, and they are on your formula sheet, so you don't have to memorize them because they're there for you. You just got to know when to use them and how. And the how is normally a substitution, right? So we're going to look at some more identities today, sum, difference, and double angle identities. And we'll verify some identities numerically and graphically using technology. So these are the sum identities, that the sine of a plus b equals the sine of a times the cosine of b plus the cosine of a times the sine of b. So whenever you have the sign of the sum of two identities, you must use this in order to find out what the value of that is. You've also got the sum identity for cosine and the sum identity for tangent. These are on the formula sheet, so you don't have to memorize them. And then you get the difference identities by taking the sum identities and replacing b with negative b. So in the case of the sine of a plus b, to make that become sine of a minus b, you replace the b with negative b. So it replace that b with negative b, this b with negative b, and that b with negative b. And so that is down below here, the steps for that. Now, after replacing the b with negative b, to go from this step here to this step here, here's what happens. When you have a negative rotation angle, that's going clockwise, okay? And when you go clockwise, the first quadrant you get to is the fourth quadrant, which you might remember is the C quadrant from the cast rule, which means the cosine is positive. That's why the cosine of negative b became the positive cosine of b, because that negative b puts you in the fourth quadrant. Yes, sir. Over there underneath, I think right beside, be the second stack. Okay? But the sign in the fourth quadrant is negative. So that's why this sign of negative b became negative sine of b, which made this negative cosine sine b. Now again, you don't have to remember that because you're given the sum and difference identities on the formula sheet. But that's where those difference identities come from. They take the sum identities and they replace b with negative b, and they become the difference identities. Okay? If you take calculus, you'll see the proofs for these sum and difference identities. Okay? You'll see those. But it's not something you need to know for the Math 30-1 curriculum. And then in the same way, to get the sign of 2a, you replace the b with the a from the sum identity. You replace b with a, and that's where this comes from. And then the sine of 2a, which is sine of a plus a, becomes the sine a cos a plus cos a sine a. These two terms are the same terms. The factors are just reversed, but they are the same thing because whenever you multiply, order doesn't matter. So you can write this second term as also sine a cos a, which gives us two sine a cos a's. Okay? And the cosine double angle identity, cos 2a, can be written as cos squared a minus sine squared a. Again, it's found by taking the cosine of a plus b and replacing the b with the a. That'll give you this expression. And there's also tan 2a. Okay? So there's our three double angle identities for sine 2a, cos 2a, and tan 2a. And once again, they are on the formula sheet, so you don't have to memorize them. You just got to know how and when to use them. And we're going to see that there are a couple of cases, a couple of situations where you will use these identities. One of them is something like this. Simplify using sum, difference, and double angle identities. The first one, write each expression as a single trig function. So for question A, you need to recognize the pattern. If we say that because the 48 degrees occurs in both terms, the 17 degrees occurs in both terms, if we say that 48 degrees is A and 17 degrees is B, you see this follows the pattern sine A cos B minus cos A sine B. That's the pattern that is followed there. And if we look back, sine A cos B minus cos A sine B is this one right here. That's the difference identity for sine. That's the pattern. So that is equal to the sine of A minus B. So if we go back to our original expression, that will equal to the sine of 48 take away 17, or the sine of 31 degrees. We were asked to write it as a single trig function. We've done that. We have done that. Now, just to show you that this is correct, that this is true, we can take our graphing calculator. We can make sure that we are in degree mode. The original expression is the sine of 48 degrees, close the bracket after the 48, times the cosine of 17 degrees, close the bracket, minus the cosine of 48, close the bracket, times the sine of 17, close the bracket, is that value. It's an irrational number. We've said that that expression is equal to the sine of 31, so the sine of 31 should give us the same irrational number, and it does. So that shows you that that is correct, that that relationship is true. Shows us that. So again, you should never get these wrong because you can always use the calculator to compare. Make sure the answer you get is equal to what you started with. Looking at question B, it is cos squared pi on 3 minus sine squared pi on 3. So the two angles are the same. So that would be the same as cos squared theta minus sine squared theta, or cos squared A minus sine squared A. And if we look at our identities, that is that one right there. Cos squared A minus sine squared A is equal to cos 2A from this double angle identity for cosine. That matches the pattern. Cos squared A minus sine squared A. So cos squared pi on 3 minus sine squared pi on 3 is equal to the cosine of 2 times pi on 3 from that double angle identity, or the cosine of 2 pi on 3. We've written it as a single trig function, which is what we were asked to do. Again, we can confirm that. We can check that on our calculator. In this case, we need to be in radian mode. The cosine of cos squared pi on 3 means the cosine of pi on 3 all squared. So close the bracket after the pi on 3, close the bracket on the cosine of pi on 3. We square it, minus, and we have to square the sine of pi on 3. Close the bracket on the pi on 3, close the bracket on the sine of pi on 3, and square it. So that gives us an answer of negative 0.5. Well, we said that's equal to the cosine of 2 pi on 3. And it is. So our simplified expression is equal to the original. We just showed that. All right? So the ones below, again, write each expression as a single trig function. So the first one, the pattern is cos A, cos B plus sine A, sine B. Right? If we replace 88 with A and 35 with B, that's the pattern. Cos A, cos B plus sine A, sine B. So if we look on the previous, that is the difference identity for cosine. Cos of A minus B is cos A cos B plus sine A sine B. That is the difference identity for cosine, the cosine of A minus B. So this equals the cosine of A minus B. So if we take our original expression, that will equal the cosine of 88 take away 35, or the cosine of 53 degrees, which again, we can check on our calculator. We have to be in degree mode because our angles are in degrees. If you take the cosine of 88, close the bracket, times the cosine of 35, close the bracket, plus the sine of 88, close the bracket, times the sine of 35. It's that irrational number. Well, that should be the same thing as the cosine of 53. And it is. So it shows that our simplified expression is equal to what we started with. Part B, the angles are the same. So that'll be 2 sine A cos A. If we replace pi on 12 with angle A. 2 sine A cos A. If we look back at our identities, that's the double angle identity for sine. That's sine 2A. Sine 2A is equal to 2 sine A cos A. So this is equal to sine 2A. So our original expression, 2 sine pi on 12 times the cosine of pi on 12 will be equal to the sine of 2 times pi on 12. And 2 pi on 12 reduces to pi on 6. So there's our answer. We've written it as a single trig function. Once again, we can check that on our calculator by going into radian mode. The original expression is 2 times the sine of pi on 12. Whoops. Two times the sine of pi on 12 times the cosine of pi on 12. Is that decimal? That should equal the sine of pi on 6. And it does. So they are equivalent. What this also does, you should recognize, in some cases, it's going to allow you to work with angles that are not on the unit circle, right? The angles for this original identity are pi on 12. Pi on 12 is not on the unit circle anywhere. But we see by using the double angle identity, that is equal to the sine of pi on 6, which is on the unit circle. So this is going to allow us, these identities are going to allow us in some cases to find the exact values of angles that are not on the unit circle. Okay? And that is something that we will be doing as we work our way through this chapter. There are alternate forms for the double angle identity for cosine. Okay? The one that we saw earlier that's on the formula sheet is that cosine of 2A is cos squared A minus sine squared A. We've already looked at that one today. That is one of the double angle identities for cos 2a. However, there are two more that we can use, and they are actually on the formula sheet. And they come from the Pythagorean identity. The Pythagorean identity says that sine squared a plus cos squared a equals 1. That is the Pythagorean identity that we looked at yesterday. And I said this is one that you're going to use quite often. Okay? You're going to use this one often, but there's also variations of this that you're going to use quite often as well. And one of them is that if you take this original Pythagorean identity and you subtract cos squared a from both sides, you'll get sine squared a by itself on the left equaling 1 minus cos squared a on the right. That's a variation of that original Pythagorean identity. And you will use these often. Not only the original version, but also this variation. But what it also allows us to do, it allows us to take what sine squared a equals and plug it in up there in the double angle identity for cosine. So now we can say that cosine 2a equals cos squared a minus all of sine squared a, or all of 1 minus cos squared a, which is why I put it in brackets, because you're subtracting all of it. When you remove the bracket, the 1 will become negative, the cos squared a will become positive, and then that cos squared a combines with the first cos squared a to give us 2 cos squared a minus 1. That is one of the variations of cos 2a. When we saw it earlier today, we said that cos 2a equals cos squared a minus sine squared a. That is true. But now we can also say that it equals 2 cos squared a minus 1. That's a second variation of the double angle identity for cosine. Okay? Also, if we start with the Pythagorean identity, what I did a few minutes ago is I subtracted the cos squared a from both sides to get sine squared a by itself. Well, you can also subtract the sine squared a from both sides to get cos squared a by itself. And you can take what cos squared a equals, and again, you will use this variation of Pythagorean identity as well. Not only the original one, not only that sine squared a equals 1 minus cos squared a, but also cos squared a equals 1 minus sine squared a. And you can take this and you can plug it up there for cos squared a to get another variation of cos 2a. Again, cos 2a is equal to cos squared a minus sine squared a. But we can replace that cos squared a with 1 minus sine squared a from the Pythagorean identity above. And then negative sine squared a, take away another sine squared a, gives us minus 2 sine squared a's. So there's our third variation for cos 2a. It can equal cos squared a minus sine squared a. That's one of them. We saw below it can equal 2 cos squared a minus 1. And now we see that it can also equal 1 minus 2 sine squared a. All three of these are on the formula sheet. You don't have to memorize them, but I just showed you where the other two come from. But they are all three on the formula sheet. So I've already answered the one below. The one that only involves the sine ratio is 1 minus 2 sine squared a. The one that only involves the cosine ratio is 2 cos squared a minus 1. Okay, so one of them involves both. The original, one of them involves only cosine. Again, these are the double angle identities for cos 2a. One of them only involves cosine, that's 2 cos squared a minus 1. And one of them only involves sine, that's 1 minus 2 sine squared a. All three are on the formula sheet, so again, you don't have to memorize them. But you can use them to simplify expressions, and that's what we're doing here. You've got an expression that involves both cos 2x and sine 2x. The first thing it asks us to do is to state the non-permissive values. Non-permissive values, remember, come from the denominator. Our denominator is sine 2x. Sine 2x cannot equal 0. So to find out where sine 2x equals 0, let's find first for where sine x equals 0. And then we'll work towards, from that, finding the answers for sine 2x equals 0. The sine of x equals 0, that's on our unit circle. We put our coordinates at the ends of the axes. Remember, sine is the second number, the y value. And that is 0 at every multiple of pi. Okay? So for sine x equals 0, x cannot equal n pi, where n is an element of integers. Every multiple of pi. So those are the restrictions if the denominator was sine x. But it's not. It's sine 2x. So what does that 2 do? Remember, using our transformations, that is a b value of 2. That causes a horizontal stretch by a factor of 1/2. So the restrictions on x will be half of what they were for sine x, equaling 0. So for sine 2x equaling 0, we would say x cannot equal n pi over 2, half of what they were before. The restrictions for when sine of x equals 0 are every multiple of pi. Then for sine 2x, that is a b value of 2, that causes a horizontal stretch by a half. Everything will be half of what it was before, including the restrictions. X cannot equal n pi over 2, where n is an element of integers. So there's our restrictions. Part B then says simplify the expression to one of the three primary trait functions. So starting with the original function, we're going to simplify. So when we replace the cos 2x, we have options. We can use any one of the three that we have at our disposal. They're all three on the formula sheet. It doesn't matter which one you use. Some of them will be easier than others, but it doesn't matter which one you use. If you use the first one, that cos 2x is cos squared x minus sine squared x. And notice I'm putting it in brackets because I'm subtracting all of it from 1. And so that's important. You're subtracting all of cos 2x from 1, so all of cos squared x minus sine squared x from 1. So again, we have three options for cos 2x. That's just one of them. You can use the other two. They'll both work. Okay, one of them might be easier than the other, but they will all work. And for sine 2x, there's only one option. Sine 2x equals 2 sine x cos x. Again, it's on the formula sheet. You don't have to memorize these. So to simplify this, on top, I'll remove the brackets. I'll get 1 minus cos squared x plus sine squared x. Right? You have a minus sign in front of the bracket. It changes all the signs inside. At this point, we cannot cancel anything out, because you can only cancel if there are the same factors in all the terms. And right now we have three terms on top. There's only one term on the bottom, but we have three different terms on the top. and those terms do not all contain the same factor. So there's some more work that we need to do. And what I'm going to key on this part of the top. What does 1 minus cos squared x equal? What does 1 minus cos squared x equal? Say again? Sine squared x, that's right. Remember we saw up here that cos squared a equals 1 minus sine squared a. And then we saw that sine squared a equals 1 minus cos squared a from that Pythagorean identity. And that's the one we're going to use. 1 minus cos squared a is equal to sine squared a. So 1 minus cos squared x is equal to sine squared x. Plus another sine squared x is going to give us 2 sine squared x on top. And now we can do some canceling, because now we have a single term on top and a single term on the bottom. We can divide top and bottom by 2. They will cancel. We can also divide top and bottom by a factor of sine x. And so we are left with sine x over cos x, which is tan x. So we've simplified it to a single trig function. And again, I did it by substituting cos 2x. I substituted that for cos squared x minus sine squared x. I could use one of the other two ones for cos 2x. I could have used 2 cos squared x minus 1. I could have used 1 minus 2 sine squared x. They would all work. Some of them might be a little easier than this one, meaning fewer steps, but they would all work. Okay? And then we can verify using technology, verify that the original expression is equal to what we started with. We've done this before by showing that the graphs would be the same. So the original expression in brackets to keep my numerator together is 1 minus cosine of 2x. Close the bracket on the 2x, close the bracket on the numerator. That's divided by sine 2x. That should be the same as the graph of tan x, because that's what we found. So right now I'm in radian mode. Let's check my windows. My windows are also in radians. So the only thing I might do is just change my windows, an x min going from negative 2 pi up to positive 2 pi. I'll choose a scale of pi over 2. And for y, I'm going to go from negative 10 to positive 10. Remember what the graph of tangent looks like. It goes up and down forever. There's asymptotes. The first one's at pi on 2. The next one's at 3 pi on 2. So now when you graph, it's going to happen fast. The two graphs directly over top of each other shows that our simplified expression is equal to what we started with. If the graphs were different, that would mean that our simplified expression is not equal to what we started with. But the graphs are the same. So our answer is correct. All right, so looking at this next one, we have an expression, sine 2x over cos 2x plus 1. First thing we're asked to do is state the non-permissive values. So they will be where cos 2x plus 1 equals 0, or where cos 2x equals negative 1. So like we did before, let's first find where cosine of x equals -1. Remember, that's from our unit circle. Cosine is the x value. It equals -1 at pi radians. So x cannot equal pi radians. Plus 2 pi n. Every multiple of 2 pi n from pi is where cosine is -1. So those are the restrictions for cos x. For cos 2x equaling -1, again, that 2 causes a horizontal stretch. A horizontal stretch by a factor of 1/2. So everything will be half of what it was before. So x cannot equal pi over 2, but also the 2 pi n will be half of what it was before. So our restrictions will actually be that x cannot equal pi over 2 plus n pi. There's the restrictions for that one. And this is a little bit different than the previous ones because the previous one we started with every multiple of pi as a restriction. We had n pi. Whoops. Yeah, it's at the top here. So we didn't have something plus 2 pi n. So that's why this one looks a little bit different with our restrictions. There were 2 places on the circle, and they were pi radians apart, where sine of x equals 0. In this case, there's only one spot where the cosine of x is -1. So that's why restrictions look a little bit different. Part B, simplify the expression into one of the primary trig ratios or functions. So we'll start with the original expression. For sine 2x, we have only one option. That's 2 sine x cos x. But on the bottom, we have 3 options for cos 2x. On the last one, we use cos squared x minus sine squared x. We can also use 2 cos squared x minus 1 or 1 minus 2 sine squared x. I'm going to use 2 cos squared x minus 1. And the reason I'm doing that is because the minus 1 will cancel with the plus 1 that's already on the bottom. This will make things a little bit easier. The other 2 ways will work. They will just involve a little bit more work than this one. So right now I can't cancel anything because I have more than one term on the bottom. However, when you cancel the 1's, because minus 1 plus 1 is 0, now you have only one term on the bottom. And now you can cancel. You can simplify. You can divide top and bottom by 2. You can divide top and bottom by a factor of cosine x. So that'll leave us with sine x over cos x, again, which is tan x. That's the same that the previous one simplified down into. So if we're going to check this on our calculator, we just have to change the first equation, which is sine 2x divided by, and again, I'm going to put the denominator in brackets. It'll be cos 2x plus 1. So I should get the same graphs again. And I do. So that confirms that our simplified expression is equal to what we started with. I checked it between -2 pi and +2 pi. It did say to just check it between 0 and 2 pi. It doesn't matter. You can see that on our graph that between 0 and 2 pi, they're the same graphs. Okay, I want you to spend some time practicing working with these sum difference identities, double angle identities, by working on page 306, questions 1, 2, and 5. Again, this practice is important. It's going to help you when it comes time for your quiz on this chapter. Okay, still waiting for a few people to write Chapter 5 quiz, and I'm waiting for one person to write Chapter 4 quiz. So until that's done, we can't go over those quizzes. We will as soon as we can. Okay, yes, sir. Yep. The stuff's in the package, isn't it? Should be. Okay. So work on those questions. The practice is important. It's going to help you when it comes down to the quiz on this chapter and also when we write our unit exam. And this trig exam will probably be the toughest one of the course. There's a lot you have to know for trig. Okay, so this practice is really important. It'll help you when you're getting ready for that exam because it'll be more fresh in your mind by doing the practice. So, Sathuni, do the damn practice. I know you do.
Why are you saying that?
Because I didn't want to make other people feel bad. I don't mind making you feel bad, though. It's kind of fun. All right?